We are recording today's presentation. We have developed our webinar series to deal with some of the technical and administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex, and we're always looking for ways to support the technology industry. Before we begin, I want to go over a few housekeeping details. First, hopefully everyone can see the title slide on your computer for the Military Standard 461G updates. This presentation is part of our webinar series presented this calendar year. We have muted everyone's microphone to keep the meeting quality as high as possible. A recording of the presentation is underway and will be sent to all attendees. A training certificate is sent to the attendees of the live presentation. And a full screen view may be preferred. Just select View and Full Screen from the drop-down menu, and Escape will allow you to return to the normal view. We encourage questions during the presentation. You can submit a question by enabling the chat or Q&A icon at the top or side of your screen and typing your question to the host. We will go through all the questions at the end of the presentation as time permits. We'd like to hear from you. You can see our contact information, and please reach out to the Academy email address at academy@wll.com or to the speaker directly. We estimate that the bulk of the presentation will take about an hour, and we will allow some time for questions at the end. I'd like to introduce you to today's speaker, Steve Koster. Steve is the president of Washington Laboratories Limited, and he has over 30 years of experience in testing systems and devices for regulatory compliance. His expertise spans a full range of product evaluations from IT, medical, machinery, measuring and communications, including wireless. He heads the Washington Laboratories team accomplishing all manner of product compliance evaluations. So now I'm going to hand it off to Steve.
Well, that was a nice introduction, Mark, for Steve Koster, but that's not me.
I'm sorry. My apologies.
No problem. I will, if you'll hand me, I've got to draw. I'll go ahead and start activities today. I'm Steve Ferguson with Washington Laboratories. Today's presentation is on Bell Standard 461G updates and how it affects the test programs that you encounter in your laboratory or when you visit the laboratory. Several new items have come about, so that's our purpose in reviewing today. Quite a few things happened as far as configurations and measurements. 461G came out in December of 2015, and we've noticed that there's been a lot of information that's been sent out and discussed, and it's not always the most accurate. We've had specialists in the field give various interpretations. So guess what? You're going to get to hear mine, and I believe what I'm saying here can be supported by a review of the standard. Two of the tests got added to the thing, CS117 for induced lightning information, immunity, shall we say, susceptibility, and CS118 personnel-borne ESD, electrostatic discharge. CS106 was deleted because it wasn't supported by the group that placed it into 461F. They evidently felt that it wasn't producing the answers they were looking for or the differences. There's a lot of things changed in conjunction with the test, but many of the general requirements in Section 4 changed regarding configuration management, test equipment, calibration, threshold measurements, and things of that nature. We will review those items as we go. And one of the things that really comes to mind here is in Section 4.3.11, the statement, and I quote, after the initial calibration, passive devices such as measurement antennas, current probes, and LISNs require no further formal calibration unless the device is repaired. The rationale was that the measurement system integrity checks is adequate to determine acceptability. And in general, I agree with that. But what we're doing is we're adding measurement checks with a lot more depth. So now the measurement checks are done on a test-by-test basis instead of routinely doing the calibration. So the cost is somewhat increased in accomplishing the test. Maybe there's a reason to do that, and it does provide a check at the time, prevents a little bit of the recall activity where you might use a device for 8 to 10 tests before the recalibration shows that a flaw had been incurred. One of my main concerns is passive antennas. If the system check is accomplished without the antenna being in place, so we don't have a good means to know that the antenna did not change. Some corrosion or something on connections could in fact have an impact, and that would be the case. Now, the stub radiator test is usually used to check reception, but a known signal level is not required. In other words, find something. I suggest that maybe when you're doing the stub radiator test, you want to physically locate a radiator at a fixed location that's always used, and the receiving antenna that you're checking at a fixed location. So these checks have meaning, and you can record what the values were originally and start seeing if you have variances indicating that your antenna performance may not be so correct. It's always been a concern that our antennas are doing the right thing, and it's pretty easy for minor things to creep in without us looking at that. So in looking at the calibration, it's not an automatic pass to get rid of that. For instance, a current probe could have a fracture or an anomaly that doesn't show up at the selected frequency. So we have to be very cautious about what we're doing here and don't blindly look at this as being the end-all. Configuration things in general, they have changed somewhat, shall we say. We notice that in the star there that I'm showing, it indicates that the cables tend to come out the side there. And a lot of people have indicated that that is the desired position simply on the diagram. Well, the standard doesn't support that in the text. The standard says you need to orient for the maximum signal, emissions, or vulnerability. So cable routing could be significant where the connector may need to be pointed towards the antenna. Now, the idea of this was to keep the cables at the same location behind the ground plane as you have everything else, instead of having a bend radius cause the cables to stick out, or the EUT, the test article itself, be recessed far away from the front edge, or from the 10 centimeters behind the front edge. So the idea is that we need to take this with a grain of salt, and quite often this configuration gets out of hand if we do that. Now, in the area it shows, I particularly chose an item with no ground plane, or an elevated ground plane above the ground plane. So the 5 centimeters height for the cable routing is above there. Now, if you do not have a ground plane associated with your test article, in other words, it's a tabletop that is used in a handheld mode or something, but it still has a LISN connected, you need to provide a partial ground plane for the LISNs to be grounded and tied to the enclosure, but the rest of the table has nothing there, and the cables are placed onto the surface of the table. And the height is still 80 to 90 centimeters, so nothing's new there. Still, when it changes to the diagrams here, in general, the drawings do not reflect the fact that an anechoic material is located typically behind the ground plane, and they show these nice little short straps that are located. Let me turn on a pointer here. I think I could use that kind of thing. Bear with me. No, I got the wrong button here. There it is. There's your pointer. We can see that the ground plane is present and the lisms are connected. But this nice little ground strap I was referring to shows a very short, tight location, but with the requirement for the ground plane to be 30 centimeters at least from the back wall, that strap is going to be somewhat lengthy, and normally we have to have a place to connect it to the shielded enclosure wall. So paying attention to that little element says you need to put in some very wide or 5-to-1 ratio to minimize the inductive reactance for the RF. Even though the bonding may be good, the RF performance needs some good low inductance. And by the way, like normal, using multiple straps, a parallel inductance reduces the overall inductance, just like a parallel resistor would. Make sure I got this thing. And so we need to bond it to the enclosure wall with less than 2.5 milliohms. Like I said, the diagram omits it, so the straps need to be looked at. The cable arrangements retracted from the front by 10 centimeters. So the cable establishes our boundary, our test boundary, not the ground plane itself, but the cable location is the front edge of the test boundary. And that should be 10 centimeters back from the ground plane at least. Elevation of 5 centimeters to expose 2 meters of cable. And note that the 2.5 meters of power cable is what's specified, not as used. Other cables can be any length that's actually used, but you don't have to go above 10 meters of cable. So the signal's there, so you don't need to exceed the actual. The power cable is required to be unshielded. Now, there's some exceptions to that, in the fact is if you're getting power from another EUT where power isolation is provided, then the cable can be shielded if it's done that way in the actual installation. But remember always that this configuration is showing a generic kind of arrangement. If you've got a particular configuration that you actually use, like you're incorporating something on a dashboard of a helicopter dashboard would be a more appropriate test configuration. So your mock-up would exactly emulate the cable layouts, and etc. So a tailored configuration matching the actual should be a preferred method to go through this thing. For the non-conductive, as I was indicating, the ground plane is not there except for the lism, the portion that you need to take care of. So basically, all the other words are the same, etc. The cable routes are above the ground plane. A freestanding configuration is very similar, except a cable is now incorporated to lay out the cables. This is going to have a significant impact on cables that used to be routed 5 centimeters above the floor. This loop area for a ground plane between the base of the EUT and the actual ground plane of the enclosure is now a much bigger loop area, and the potential exists for higher level emissions because of that loop area. Especially common mode emissions are going to increase dramatically. So the freestanding thing shows that, and it's the same as the general one except this tabletop routing. And remember, the vertical cable is not part of the 2-meter exposed cable. The cable ground plane is attached to the shielded enclosure, and so is the UT, but we do have a loop configuration that does exist with this. The UT is grounded to the enclosure, so the strap is there. It's restricted if it's not part of the installation. Now, this is the thing that gets away from us pretty easy. We attach artificial grounds because this generic configuration shows one. If that rack is not grounded any place, it should be placed on the isolation and 10 centimeters, 5 centimeters above the ground plane without a direct connection. If it's not part of the installation to put a ground strap in, you should not do it. The ground should be what you install. It should match the installation. And the rotation of the UT presents some cable routing challenges, but that's not discussed. Remember, I need to turn this thing around for maximum exposure. And that's not just for the conducted test or the radiated test. We need to configure it that way so coupling can be portrayed. For an outdoor configuration, we have a similar thing to the tabletop, except suddenly the cables look like they come out the side, but they could be coming out the top or the bottom or wherever they need to egress out of the freestanding configuration. And it only shows some power cables going to the unit as an outdoor. But we can have outdoor units that connect for signal cables and the like. So don't think just because it's kind of showing a generic that you don't have to connect them. And also, one of the key elements is 2.5 meters of exposure here on the ground plane for the outdoor equivalent. The ground plane area between there and the ground plane edge need to take care of that, and the antenna needs to be placed within that boundary. So basically, it's the same as with the tabletop routing, etc. And remember, the vertical cables are not part of it. And by the way, vertical don't necessarily mean coming from up high. It could be coming from below to up. And our antennas are based on exposure to the UT. The ground's a ground plane thing. The UT step is indicated, but remember, it's not there if it's not used in a real installation. Bonding about drives me crazy with some of these things, and they did some work on this thing in the standard. It needs to verify that the bonding of the ground plane to the enclosure. That's been there forever. And that's 2.5 milliohm requirement. Between the ground plane and the enclosure wall is a 2.5 milliohm junction. But the UT bonded out of section 4.3.8.2 says only the provisions included in the design shall be used. So what does that really mean to us? If I've got a rack of equipment that gets plugged in via an AC power cable, and that green wire is the only connection made, then that's the only connection that should be present during the test. And we know that a 2-meter power cable is going to be greater than 2.5 milliohms, so people applying this 2.5 milliohm requirement and forcing other grounds to be installed during the test are giving us fake answers. The verification in the text calls for you to measure the grounding situation without additional grounds. So that indicates that you need to measure what you have installed with the ground connections that are used made, but not other grounds like shielded cables and the like that give us a parallel path for the bonding. We need to measure what it would be prior to all those actual things and record this in the report. The value is not defined, it needs to be what it is. So you should always consider using this as a means to say, I am matching the installation and my results of the grounding are indicative of what the actual installation is. Now, if you have a shielded cable that must be installed, no ifs, ands, or buts, it's not an optional cable, it's there, then you may be able to include that as part of your grounding scheme, only if it's going to be grounded that way in the real installation. So don't put artificial things in here. And we can apply this to a lot of cases. Remember, it applies to the ground plane connection, not necessarily 2.5 milliohms. This 2.5 milliohm requirement throughout history has been misapplied over and over again. I've had many, many instances where the witness or the representative, the government office, says you make it that way, and they have no intention of installing it that way, even though they just misapplied the bonding requirement because of a lack of interpretation that comes from really Mill Standard 464. Threshold measurements came about. Previously, there was no requirement defined on how many we should take. Approval could require many measurements if you had a large frequency range or at each step along your item where susceptibility was noted. Section 4.3.10.43 says you need to determine worst case and record the frequency range and the frequency and level of the greatest susceptibility. My personal thoughts is that susceptibility is seldom a Gaussian distribution. So having the 1 point as worst case don't necessarily mean how other frequencies in the end are going to react. I like to look at a range with the greatest, the overall frequency, the greatest value, in other words, the most susceptible, and 2 to 3 points per octave over the range of susceptibility. This gives us several data points without going to an extreme on it, but it lets the designers know what's going on with this thing, the magnitude and what it is. And remember, when you're doing threshold measurements, each threshold indicator needs to be addressed independently. So a worst case for the fan stopping and a worst case for the light blinking may be two entirely different issues going on here, but they may cross over somewhat. So threshold measurements finally are seeing some reality that what people will actually do. So typically, like I said, I like to do a few more, but not going overwhelming. A threshold chart may need to be dealt with where you see that I am applying a signal that's above the limit line. This happens to be for CS101, and a way to record what the threshold of susceptibility was. So your data system needs to be allowed to do that. When you're taking threshold measurements and using automated testing, you need to have a way to go interactive, because the automated tool may not know how your unit is reacting. You need to look at where your unit can recover or anything like that. So, but the idea is that we don't necessarily have a ton of things to do, but you need to record the good data points, several points there. That particular chart is a little Excel sheet that we use for manual measurements in this area. Help us get some of this when the automated tool is inadequate to support us. The FFT Receiver function got approved in this thing. Previously, it was step tuned only, with the measurement time minimum based on the UT cycle time. Well, what does that mean? That means that if the UT took 2 seconds to do its function, we needed to be at each point for 2 seconds, or at each half bandwidth measurement, in order to meet the 2 dB accuracy. We needed to overlap the bandwidths by about half to get down to this 2 dB accuracy. If we allowed a full bandwidth step and an event happened between steps, the 6 dB bandwidth could produce a 6 dB measurement accuracy, which is insufficient to meet the overall requirements. Now, that's all well and good, and it takes a long time to switch through some of these things, especially when we have a long measurement time or long cycle time. The FFT Receiver came out, it meets the C63.2 requirements, but it's the time bandwidth minimum defined as the UT cycle time needs to be considered. In the standard, let me check, see if I've got it. Yep, I do have it. I'll get to there in a second. It's defined, but the UT cycle needs to be considered. The user interface must support parameters to input control of this. Now, if we look at the chart here, we'll see that the FFT Receiver has got a 1 second per bandwidth, okay? So that's okay, but that was based on the sample where it had a 1 hertz signal being captured. So if you have a 0.5 hertz, that needs to be up to 2 seconds per. So the cycle time rules no matter what. The UT cycle time needs to be considered. This 1 second was based on a program to get this accepted that used a 1 hertz thing, and realized that you could see the FFT function translate the transient or the event that happened into a frequency that was required to produce that kind of an impulse. And this modeled out to be very good for this. I've seen demos of this and work with it. It's fantastic for catching transient events that have been always elusive in doing the step or dwell time tune things. It's very difficult to capture that. So we need to stay there long enough for the events to happen. Some terms came into being as part of the 461, which is exposed below deck application got introduced. It's there, and the application of it is not really clear. The exposed below deck application was introduced to prevent over-testing and the susceptibility, where the hangar deck, for instance, of a ship provides some shielding effectiveness so the overall exposure to topside transmitters are not going to have the same effects. We do have some clear segregation for this thing, or a low-level test. But this needs to be worked out as part of your overall test procedure, and you take any information you have on the actual platform and work with it. There are some other things considered, like the bridge of a ship may see this kind of activity, but the bridge is such an open area with windows that is not treated for shielding or even a wire mesh shielding that needs to be considered as exposed totally, not below deck. We've seen a lot of activities that the Navy gets presented this thing as the bridge presents shielding. That should not be considered. I do want to put a couple of things together about some cables. It's not new, but they talked about the cable bundle in 461G as associated with the DUT connector. Well, that is true. But what about a cable connector where the wires are routed to separate directions? It comes out of a connector and part of the wires go to the left and part go to the right in the actual installation. Do you think that each side of those cables are going to be exposed to a common mode signal? One's going to be higher or lower than the other, and we'll see a differential mode vulnerability. And if we don't segregate those cables when emulating it for the conductive equivalent, we will be falsely approving the product because the common mode is not really present. And another thing is the cable back shell part of the EUT or part of the cable. The cable back shell is stated in the standard, but most people kind of can't find it. If a cable back shell is greater than 50 millimeters, then it is part of the cable. If it's less than 50 millimeters, it's part of the EUT. In other words, the EUT actual shell comes out 50 millimeters if the back shell is that way. The loading, again, this is not new either, but it's often incomplete. All electrical input and output interfaces shall be terminated. The EUTs and the mechanical outputs shall be suitably loaded. And when a variable electric or mechanical loading is present in the actual installation, testing should be performed under the expected worst-case conditions. That being said, let's take an example that I always tend to fall back to, a windshield wiper motor. It needs to be loaded. Well, how do you load it in the lab? Well, you have to put a windshield wiper on the motor. How about you have to put it against a piece of glass? Should the piece of glass be wet to simulate the proper loading? Well, I suggest that you can take care of this by a physical weight or something that's being picked up by the motor turning and having the weight equivalent to a loaded windshield wiper. You may need to install one to determine what kind of currents you're drawing, and once you meet that same current, you have an equivalent load function. Pumps. Pumping air is not the same as pumping water. The load on the pumps are not the same. So we need to consider the loading effects of the mechanical associated events. Again, it's not new, it's there. Now let's get into a few of the details on the testing itself. CE101 Limit relaxation came about, and they changed slightly on how they define these things. For the DC or 60 hertz greater than 1 amp, or if it's less than greater than 1 amp, then it's set for 400 hertz. But it's basically 20 log of the fundamental current. And for DC, if it's greater than that, you can do that with a maximum relaxation. Aircraft, that particular limit for that had no relaxation provided. That's typically not very realistic unless these are low power, low current draw devices. If I've got a piece of equipment that's drawing 40 amps and it's on an aircraft, do you expect the second harmonic to be that clean based on a 40 amp fundamental without relaxing the limit to allow for the fundamental? I suggest that we need to consider this, and if you have this application, you might want to, in your test procedure development, consider this and calculate a alternate limits, so you're not having to fight a battle during the report review that you had to relax it, and now you're looking for a waiver or deviation, and nobody wants to look at it then. If you're going in with a fundamental position that shows relaxation is going to be necessary, or you're going to have to expand the physical filtering things so big that nobody wants it on an airplane, then you need to crank that into your test procedure. High current issues came about. The installation may produce some voltage drops. Remember, the LISN does see this, especially for the high current, etc. And it can become more significant with 400 hertz power. So 461F introduced it, and G continued it to use an alternate LISN, especially use of the 5 microhenry LISN for the situations. It requires overall tailoring for CE101 and 102. And even if CE101 is not used, normally you may have to pull it into the fray to allow this alternate limit. The discussion in the standard is very good about how you need to adjust for it. It's in the appendix, but it provides excellent guidance on compensating for the gates. Again, the appendix is not contractual, so your procedure needs to account for it through the approval of that process. That's a contractual element. CE102 Calibration came out. They changed the frequency suddenly here, 10.5 kilohertz instead of 10, 100 kilohertz, 1.95 megahertz instead of 2, 9.8. And the best I've been able to figure out is that you needed to get this thing off of a frequency where the graph had a line that you couldn't see your measurement easily, except 1 kilohertz didn't get hit. There's a line there too. So I suggest that your procedures do that. We've done that forever. We go off that frequency slightly to allow the charts to show the actual signal measured. And remember that the determination for the oscilloscope voltage are to be set. Remember that the 10.5 100 kilohertz are below the 50 ohm impedance of the standard LISN. So you need to measure the signal, because if you just connect the signal generator, the LISN will load it, and what the signal generator says is not what's really being applied. Set the generator modules based on the oscilloscope. Also added as part of the completeness for this no calibration of the LISN, you need to validate that the loaded versus unloaded is 14 dB or 3 dB, depending on the frequency of interest there. So you measure it, and then you load and unload this to see that the variation changed by that amount. It works if everything's in order. So, but the idea is now I've got this other step going on to maintain my calibration function. CE106, they do a lot of work in CE106, but no significant changes here. But I didn't want to throw this thing in because if I'm not operating my receiver system in the linear region, I overdrive it because some transmitter was creating this and I didn't notch the filter out properly. I get the upper trace here that I'm pointing at. All of these spurs and harmonics going on. The same test, and this happens to be a 15 megahertz test, has similar things going on, except we notched out 15 megahertz and added the notch attenuation back as a correction factor, and suddenly the performance is down below. No change to the UT. It's the fact that we allowed overdriving of our amplifier in our receiver system to cause nonlinearity. So it's a problem. Be aware when you start seeing this stuff, it may not always be a failure mode. CS101 incorporated a few changes also, or it's applicable to power leads, and now it's less than 30 amps per phase unless there's a particular vulnerable requirement. Previously, it was 100 amps, okay? And before that, it didn't have a measurement, so it's always good to know this. At 30 amps, good amplifiers won't reject your feedback, so you don't run into so many problems. And again, the measurement receiver can be the FFT, and you need to get a measurement transducer. The transducer is used to isolate the power lines. These are commercially available, but they're not specified as to which ones are what. If you choose to do this to more readily automate your testing, then you need to consider that as incorporated in and get the right correction factors, etc. Phase shift networks are permitted or not permitted as the transducer. So these transducers allow for more automation control. For CS101, in order to do this, we either overdrove it based on a pre-calibrated drive level, or we didn't attain the right levels. And recording data was always a pain. It's feasible to do this without that measurement transducer. You can do this through witnessing and looking at the modulation characteristics versus the actual fundamental power frequency. Difficult at times, but it can be done. Less than 10 kilohertz, there's a voltage drop across the power source that may dominate everything. The 10 microfarad feed-through capacitor is for the series source Listen bypass inductance. The enclosure filter and components may drop the voltage. So what you actually see is the voltage not being created across the UT because the shielded enclosure filter inductance drops all the voltage there. So if you don't attain the voltage with the pre-calibrated power level, then you need to locate where the missing test is. If the drop is associated with the power source or the feed-through filtering, then you need to do corrective action. Corrective action for DC can use a large capacitor in parallel with the 10 microfarad to lower the frequency of this. For AC, you may need to bypass the facility power filter or go to some other source. So fundamentally, that's what's going on here. My primary load is to measure what I'm dropping across the load circuit. But also, if I don't attain that voltage, by the time I get to the drive level, I need to measure what's going on across the listen for it, across the power source, etc., and eliminate these problems associated with that so the test voltage is maintained across the load. Remember, this is a test configuration detail, not an actual installation, so these allow you to get to a more prevalent test level. CS114 had a change to the test current. The idea is that we used to do a pre-calibrated level, or the blue line in this case, and this was the test calibration drive level. The testing was done 6 dB above that historically. That's because the test configuration of the test jig to do the pre-calibration used a 100 ohm impedance. So to maintain our 50 ohm requisite, we had to increase the current by 6 dB to compensate for the fact that we were using 100 ohms or 6 dB more resistance. And now the new limit says you need to go to the 6 dB above the highest level that's incorporated. So the idea is now throughout the frequency range. So we end up flatlining where the actual drive levels are there. Now, normally you're not going to actually run into this in the real world. However, some close proximity transmitters on topside ships did encounter the problem. So quite often you're going to end up at the drive level and some other current not going that high. But you could go that high, and it's potentially some cumbersome adds to the overall cost because you're now trying to clean up this signal that doesn't exist in the real world in 99% of the cases. So if I have a current that's got 3 levels going on here, I had the test current. So at frequencies below where the curve 4 applies, we'd use above 6 dB above across the whole board, or would you use 6 dB above the highest point for the 4? It's indicated in the standard that you'd use the red line and then the black line for that band for curve 4, and then come back to the red line for that, for the portion that's above 30 megahertz. That's the way the words read. So make sure you interpret it using that kind of a philosophy. The pretest calibration also changed significantly. Where we used to have a calibration jig and our terminators going on, we now incorporate a measurement probe calibration jig. So when we create the forward power to circulate through the system, we're now incorporating this, and notice that it's terminated into a 50 ohm load. So that's present, but it's not really there. So the idea is that the measurement probe is there and its function, how it affects the currents on the line is present during the pre-calibration interval. So we see this activity. It's still the 100 ohm termination here in series with the termination here. And we record the values that it took to drive that. So now when we go to the second part of the calibration, we move our monitoring receiver here and play back the drive levels that we pre-calibrated with to see that the current measured matches the test current. Now, the standard allows you to do only half of the measurements, but for an automated system, it wouldn't make any sense to reprogram for a few minutes of downtime. Now, why is this happening? This is happening because we don't calibrate the current probe. So we're using this to validate that the current probe is measuring what we told it to be. It's just a common fact. So we're doing this on a case-by-case basis instead of routine calibration of the probes. There are advantages and disadvantages, and cost control is one of them. For the CS114 test configuration, we have not much change here. It pretty well stays the same, but I pick on this because sometimes the configuration fails to look at it. Remember, those test cables are located in a configuration 5 centimeters above the ground plane. And what happens is if I don't consider the proper cable layout, my series inductance and parallel capacitance or distributed capacitance in the wire harness relative to ground plane allows currents at low frequencies to come from the injection probe through the monitoring probe into the UT through whatever connection it has to the ground plane and return currents all the way back around to the support equipment ground plane and back down the cable under test. As the frequency goes higher and higher, the distributed capacitance starts short-circuiting this current flow to the point by a few 50 to 100 megahertz, I start seeing an overall path of the probe coming to here, and it's all being reconstructed in a very short area. And as my frequency goes even higher, it's a very short loop. So if these probes are positioned in the middle of the cable, I'll start circulating currents around the center of the cable, and nothing ever affects the circuitry of the UT or the support equipment. So getting the right configuration here is significant. Believe me, I've had auditors and accrediting bodies tell me it didn't matter and tell customers it didn't matter. I want you to realize that we're trying to simulate RF energy coupled onto the cable from a radiated field. If these distributed capacitance and series inductance cause the currents to flow in a loop that's not part of the UT, we have not met our objective to identify potential problems. So consider that when determining those kind of things. CS117 is conducted susceptibility with lightning loose transients, very limited applications along for safety critical, non-safety if it's specified. Remember, these tests are accomplished by bulk cable injection, a lot like CS114 would do on the cable bundles, power cables, and the high side of cables, of power cables. The limits are defined, but specific platform data takes precedence. That should be the case to always get platform data. Various waveforms are there with a current defined or a voltage defined, a voltage limit with a current of test or a test current, or a limited current with a test voltage, several things here. Notice that there's multiple bursts and multiple strike waveforms along with the double exponential waveform you see at the top. The test levels are defined here as to what they're supposed to be with a test voltage and et cetera for the various waveforms. So if we're doing this, that particular first item there would be the case. Now these are just a few of the extracted levels out of the standard, but here's a concern. How short is short? The item says for short cables it don't apply. Well, short might be 3 meters to some people and 50 centimeters to the next person. And how low is low? If you just don't know these values here. So something has to be determined. I suggest your test procedure take care of defining this function here. so you can get agreement with you and the end user as to what it will be and what the compliance parameters are. Excuse me. CS118 is personnel-borne electrostatic discharge. This came about as a necessary evil that we've been ignoring for years in the military world. Remember, Ordnance ESD is Mil Standard 331, not this standard for the Ordnance. So paying attention to the standard and its particular parameters is there. But basically, the personnel-borne is a human body model. It emulates the IEC 61000 4-2 test program and is brought out with several test levels for conducted and air discharges. Remember, conducted discharge lets you get better control of the waveform and repeatability. Air discharges compensate when you don't get a conducted path attached, no metal structure. So you'd use this air discharge and see if it breaks through the insulation. Several things happen with calibration as far as the waveform guidance, how much current you're getting, the waveform, the tip voltage, and etc. It's pretty clear on doing that, and the test target is something that's well defined. It's extracted right out. It's the same test target as the IEC 61000 4-2. So the idea is we're simulating the same thing for this. And remember, if you consider that 464, the system document, brought in electronic assembly ESD testing prior to it being in 461, this should show conformity. RE102 saw a couple of minor changes, but it's applicable everywhere, and the tests are performed throughout the case. The start frequency depends on the application, and they're defined in the standard. But a new item here, the upper frequency is 18 gigahertz. The idea that it used to say the upper frequency was based on the UT, so you could stop as low as a gig at 1 gigahertz instead of 18. I heard it said that the reason for this is it's not significant in the amount of time it takes. Well, if you've got large EUTs that have 30 or 40 antenna positions, time becomes significant. Okay, this to me was a little bit lack of consideration, where we don't see signals because everything's operating at low speed, but yet over and over again we test up to 18 gigahertz, burning time and incurring costs in the product approval. And it's not required to transmit fundamental. Well, okay, it's not required of this, but guess what? They have you turn the transmitters on. Used to be in 461 RE102, you put the transmitters in standby, and you did the transmit function as an RE103 event. This doesn't eliminate the need for RE103, but it sure does cause a lot of transmitter elements to be showing up all over the chart, and that's accounting for them. Now, we can eliminate those frequencies by skipping over that band, but why do we want to do that instead of just turning them off? Well, the idea is the processors and software addition, radio and hopping, etc., allow some control functions, and without the transmitter active, you don't see those events either. So there's a case made for including it. I just think that we need to look at some caution here. The antenna beam width is not new, but I wanted to point out that the beam width is based on positioning the antenna so you're seeing the EUT and, depending on the frequency range, certain portions of the cable. This example shows the positioning, how we may lay out an item. So the antenna position is directly opposite that point on the chart where we say that item C is an antenna position for selected polarization / beam width calibration. You need to analyze your antenna beam width, your UT size, its distance to the UT, and etc., and provide for multiple positions to make sure you've covered the whole range. This becomes even more significant as the higher frequencies are required to be tested even if there's not a potential issue. So in general, the requirements are often assumed instead of confirmed. So a lot of these general things, like the impedance of the ground plane. The guidance on the common test parameters are provided, but some elements have a significant impact on results and especially repeatability. For instance, the cable positioning for CS114, 115, 116. I don't analyze everything in the thing as minor things that have changed, but lack as much significance. I try to cover these bigger areas here today. And so the test methods have many changes, some related to changes in calibration requirements. And again, tailoring is particularly applicable to the limited application test zones. If I have something that's only used in a below deck, shipboard, hangar deck only situation, that's the only place it's ever used, then I may want to tailor it for that particular application, limit it to what we're doing so we don't incur cost. Remember, if we do a test and it shows a failure, we have obligation to resolve it. And if it failed during the initial test, you say, well, that don't apply to us anyway. That's not the time for the case. Do this in your planning stages. Set up your tailoring appropriately and do the right thing for those kind of things. For those that may not know, quicksearch.dla.mil will allow you to get access to the public forum mil standards. Just you can do a quick search and type in the number and it will return those things that have that number. We also put quite a bit of information on our website. And if you look at our homepage, there's a Did You Know series that's becoming more and more populated with little tidbits of questions that we receive occasionally. And we try to post the answers so it's readily available for people's consideration. If you have a topic or question, by all means, let me know. I'll try to get it on the website. And by all means, feel free to reach out to me. I hear from customers all the time with these questions. And by the way, they're not automatically answerable. If it's a major project, I'm going to ask for some payment because we sell time and services. But the idea is that minor little questions I tend to answer without even bothering with that. Or if I can't answer it, I say I don't know the answer. Okay, I'm willing to admit that I don't have all the answers going on here. And if there are any questions, I'm open for a couple. If you got any, Mark.
Well, thanks, Steve. I appreciate that. I'm not seeing any. It looks like Richard asked a question, but I'm not seeing the question. It's got the.
You may have to open up your chat or Q&A.
Okay. Yeah, let me get that done.
IEC 61004-2 has the EAD target to be used to be more than 2.1 ohms, mil standard, and I don't see the rest of the question in my window. Can you read the whole thing, Mark? It's showing up.
No, I'm not able to see it. I don't know this strange.
Okay, it says that mil standard 461 states 2 ohms, therefore 661 follows IEC 61004. I think it's confirming what I said there, that it's they're the same targets. Okay.
Okay. And there was on chat. There was a question that said, "Can you go over slide 31 again? And will the slideshow be available?"
Well, number one, the slideshow will be available, and let me get to 31. My mouse quit working for me. There's 31. The slideshow will be available along with a copy of this presentation. We have to convert to format so it's available for people. That'll take a day or two. And we'll send out a link to the recording as well as the presentation as part of what we provide to our people. CS114, slide 31 review. During the test configuration, a injection probe is placed here to the left side of where my arrow is pointing, and the monitoring probe is placed to the right side. That right side is 5 centimeters away from the EUT, and remember the back shell may or may not be part of the EUT depending on its length. But I place this next to that cable. I put the injection probe 5 centimeters away from this. This establishes our overall boundary as part of the EUT. So as we go up in high frequencies, I do actually see signals into the EUT and returning via the ground plane in a very short loop. So I'm starting to affect the EUT. what happens if these 5 centimeter height changes to 10 centimeters? Well, the dielectric of the capacitance changed, so this loop becomes shorter. I'm not coupling as well, it becomes longer. So I'm coupling at higher frequencies. It takes me more of this capacitance because the dielectric changed. If I lay this cable on the actual ground plane, then the dielectric is going to be changed, and I'll see a very much shorter coupling route for all of the currents are produced in this area. So that's kind of the importance. What if I put these cables on a non-conductive surface, not a ground plane at all, but like on a common tabletop, 80 or 90 centimeters? The dielectric has now got an error of 80 to 90 centimeters, and so the coupling mechanism requires current to go way around to get a return path. And as I do that, my series inductance increases significantly and lowers the overall current being produced. I achieve the test current, I achieve the drive level without attaining the test current. So these positioning things and cable configurations are significantly important to attaining your measured or your target goal of coupling RF energy from fields into the cable harness and inducing current flow. It could be common or differential mode depending on how it hits the circuit. It's inside the unit. I hope that provided more info there. Okay, if not, whoever it was that asked can certainly contact me for more discussion. Okay. Any others, Mark?
No, let me check one more time to make sure nothing came through while you're talking there. I don't see anything else there, and nothing else on chat.
Okay.
All right, so I appreciate all that attended today. We want to thank you for your attendance and hope we'll see you at future events. Our next webinars coming up, we've got a EMC series with Ken Wyatt and his popular EMC design series. There was one earlier today, and the next one will be on September 28th, which will be part 2 of the ground control stuff he was going over today. And then we just had our free webinar on the mill standard 461G updates, and then myself, I'll be giving a update on the hazard-based safety engineering standard on 12th of October, and that'll be our next free webinar. And we have a 4-part series on battery technology starting September 19th. Yes.
Mark, an update on that. That series was just canceled.
Oh, okay.
The presenters decided not to go forward because there was a low interest level as far as actual registrations. So they can't afford to do it for that and dropped, so I had to cancel it.
Okay. And we are working on some future webinars, medical device, EMC, and wireless device for IoT. And so if there's any subjects you'd like to see us to cover, be sure to send those to Steve Ferguson or myself, and we'd be glad to take a look at them and see if we can work up something for that. Just continue to check our website at www.wll.com for Washington Laboratories. And that concludes today's webinar. On behalf of myself, Steve Ferguson, and the entire WL Academy team, I'd like to thank you all for attending. I will now close the meeting.